sir. Am I audible, Tiwari sir?
Yes, you are. Can you hear me?
Yes, you are audible, sir. Uh, okay.
Good evening, sir. Dr. Sanjay, good evening.
Good evening, Dr. Otiwala. How are you?
Fine, very fine.
Okay. We have with us the next speaker, Dr. Sanjay Tiwari, sir. Dr. Sanjay Tiwari actively engages in pedagogical and scholarly activities as an associate teaching professor at Missouri University of Science and Technology, located in Missouri State of United States of America. Dr. Tiwari's teaching and research efforts are focused on environmental engineering. Specifically, his focus is on water quality and challenges related to wastewater treatment and issues. His recently funded projects have been in the area of pollution prevention and resiliencies of infrastructure. In addition, Dr. Tiwari has an interest in K-12 STEM education. He has a strong interest in engineering education related activities and societies. He enjoys teaching various core classes and mentoring students and engaging with engineering societies such as the American Society of Civil Engineers, American Society for Engineer Education, and Water Environment Federation. It is our privilege to have with us Dr. Sanjay Tiwari, sir. The virtual stage is all yours, sir. Please continue.
Thank you, Dr. Taylor. I appreciate it. I hope all of you can hear my voice okay. If any time there is a issue in terms of connection, just let me know and I will try to troubleshoot on my end.
Sure, sir.
I already shared PowerPoint. I'm hoping that you all can see the PowerPoint on your screen. Please give me a thumb up if
Yes,
you.
yes, sir. It is
Okay,
visible.
okay, good. So, uh, good evening, everyone. As introduced, my name is Sanjay Tiwari, and I am actually a product of your own city, Surat. I graduated from there in 2000. And I will talk a little bit more about myself and my journey before we actually jump into today's topic, that is going to be electrochemical technologies for wastewater treatment. Uh, Now, let me see if I can. My contact information is listed here along with my designation. I have joint appointment with Missouri State University here, but my main hiring university is Missouri University of Science and Technology. Uh, this is my educational background. I did my undergraduate from SVNIT in 2000. It used to be Regional Engineering College at that time. I really enjoyed my 4 years over there. It was the best time. And we still remember, anytime we get together, we still remember all the things. One of my professor recently retired, Dr. Robin Christian, and it brought some memories back of my interaction with him. Uh, right after my undergraduate from SVNIT, I did my MTech from IIT Roorkee, and I kind of took a jump from civil engineering because my interest was in environmental engineering. And IIT Roorkee, they have a very specific master's program degree, which is called Industrial Pollution Abatement. But that MTech is offered under chemical engineering. So my MTech degree was in chemical engineering, and then I did my PhD from Texas A&M University. These are my academic appointments. Currently, I am associate teaching professor at Missouri S&T. Before that, I was assistant professor, joint appointment with Missouri S&T. Uh, Even before that, I was at Louisiana Tech University. I spent 6 years over there. And then I had a bunch of short-term appointments before that, as graduate teaching assistant, graduate fellow, and even research fellow at IIT Roorkee with their alternate hydro energy center. I don't know the name if they still have the same name, but at the time it was Alternate Hydro Energy Center at IIT Roorkee. Uh, I have been traveling here and there during summer. Summer of 2020, I was at, uh, I think it was not summer of 2020, but I think it was, the date is wrong. I think I have to check. It was summer of 2022. I was in Allahabad under the GAN scheme as at MNIT. And 2019, just before COVID, the summer of 2019, I was in China at Southwest University, and we had uh, about 3 weeks long summer short course that I did over there. Uh, all these experiences, when you are stepping out from your own home country, visiting other country, and sharing your knowledge with students and experts, gives you some knowledge back. So I'm thankful of all the experiences I have. In addition to my academic appointments, I have been actively involved with consultancy and private sector responsibilities as much as I can take. Uh, I don't have much time, but during summer times, it gives me flexibility to be involved with consultancy. So I have been associated with uh, AARC Consultant Group in Houston, Texas. I take care of the hydrology and hydrogeology and climate risk department. Uh, Before that, I worked with specifically a city of Marlin, Texas, on their drinking water treatment issues and challenges they were facing. And before that, I did a couple of short-term uh, uh, tenures with uh, AFRAS, and one of the main one that I really enjoyed was Texas Commission on Environmental Quality. It's a regulatory agency, and it is considered one of the largest regulatory agency in the United States after EPA. So this is the second largest regulatory agency when it comes to environmental compliance. This is my research topic, a little bit everything, but in the field of academia, as many of you are faculty, and this is a faculty development program, uh, you all know the reality. There are going to be projects, and if you know that you have the background and experience to solve a project or give a better product at the end of the project, you apply for that. So I have written many projects, and depending on what were funded, what were not funded, I have gained a kind of wide variety of experiences. So they go from drinking water challenges to wastewater issues to biotic and embiotic remediation, sustainability and resiliency challenges that we face in today's world, applying GIS to environmental and infrastructure related challenges. And then this is the bottom one is my passion, because I am in teaching field, which is pedagogical aspect of engineering education. Um, Today will be mainly focused on wastewater challenges using electrochemical technologies. So uh, let's moving on and start uh, the actual presentation. This is my outline of presentation. I kept it short. It is going to be mainly asking big questions among ourselves. What are the things that conventional wastewater treatment are facing in terms of challenges? What are the solutions? And then we'll see different electrochemical technologies that could be as one of the options, or a combination of different technologies put together to treat the challenges or to solve the challenge, overcome the challenges that we are facing. And then we'll go one by one over their types, their applications, what are the pollutants, what is happening in each of these technologies. We'll do a little bit comparison, and then we'll conclude. So let's start with the big question. Here, thinking about conventional wastewater treatment, uh, the very first question that should everyone be thinking about, are these conventional wastewater treatment plant effective, or at least as effective as they were in olden time, let's say 40, 50 years ago, as compared to the wastewater quality right now? The general answer is yes. Yes, they are effective. They have been used in service for many, many decades, and they are doing their job pretty good. Uh, and I would agree with that. However, the characteristic of wastewater that is being collected in urban areas these days is vastly different than what was happening few decades back. These days, our sewage is not only dominated by BOD, just like it was before, and that's how municipal sewage is defined. But in addition to high organic content, we are having a higher concentration, higher pollution level of pharmaceuticals, heavy metals, organics of complex nature, and then we are talking about heavy metals. So design of conventional wastewater does a good job in removing BOD concentration, but it fails when it comes to pharmaceuticals. It fails to deal with salinity issues because these conventional wastewater treatment were not designed to deal with these kind of pollutants. Now, in recent years, within the last decade or more, you will see that there have been some changes to conventional wastewater treatment, and we have brought in some technologies, and slowly we are integrating them to handle these pollutants. During my last visit to India, when I was at MNIT, Allahabad, I visited a wastewater treatment plant operated by a Adani company at the banks of the Ganges, the river Ganga. Over there, it was right at the Sangam, actually, this plant. And they were using phytoremediation along with other traditional uh, BOD removing technologies. Uh, I did not have time to study the effectiveness of that specific combination, but phytoremediation generally is uh, a slower process unless you happen to choose species that can remove certain contamination. So just to give you an example, so people are trying different things. Now, the challenges that we are facing right now is we are discarding pills and pharmaceutical products, whether they are being released metabolically by humans or they are being dumped into our commodes intentionally because we don't want them to go. This problem is larger problem in the United States as compared to India, but still the pharmaceutical concentration, pathological issues are certainly changing the game when it comes to sewage. Now, we could use electrochemical technologies, and I will introduce them soon after this, but understand that no single technology can solve the complex nature of municipal and industrial sewage or industrial wastewater because it's by nature going to be mix of wide range of pollutants. So how can we overcome these issues? So some of the challenges specific, if I have to specifically identify, uh, inefficient or incomplete removal of emerging contaminants. We have high energy consumption and operating cost for these, specifically when we are talking about um, processes that use aeration, for example, activated sludge process. The operation cost of activated sludge process alone, aeration cost is super expensive, is really high. Uh, and then uh, you have sludge generation, the quantity, and then you need to have a specific infrastructure in place for it to digest if you're trying to get energy out of it, and handling issues coming there. The heavy metals and toxic compounds, they are always uh, not removed using conventional treatment processes. So you need some additional layer of treatment for you to take care of them. Nutrients, unless you do tertiary treatment, you will not see that nitrogen phosphorus removal effectively. Now, here is the issue. We all know the value of nutrients, but as the side effect of nutrients when they are released into natural environment body, they are well known, so I'm not going to talk about that. Uh, and then seasonal shock, daily variation, seasonal variation, too cold of a water, too hot of a season, bacteria being the workhorse, they may not feel comfortable. So the performance and efficiency of treatment is implicated or impacted by these vulnerability because of these vulnerabilities. Now, uh, I'm not sure. I don't have that data. Otherwise, I would have presented that. Uh, in terms of salinity variation, how much salinity variation is there in uh, wastewater across the India? But in US, this is a problem in many parts where wastewater is highly salinated. So wastewater treatment plants are able to remove a lot of organic pollutants, but salinity still remains, and that could impact the receiving water body. Now, how can the electrochemical technologies come and help us in these scenarios? So, understand this that the basic principle of electrochemical technologies revolves around applying current and breaking down these pollutants electrically or removing them because based on certain physical, chemical, and electrical processes. So the energy required to operate these things is going to be very low because the current that is applied and the voltage that is applied is of low amount. So that's why overall energy involvement is less. So we can remove these pharmaceutical heavy metals and microplastics easily using uh, a combination of conventional as well as electrochemical technology. We the sludge production is less because a lot of pollutants are being broken down because of current application. There is going to be a better disinfection of the treated wastewater that will come out because of electrical effect, disinfections that are being formed during the electrical process, and because of other combinations. So water requires less amount of chemicals before it is being discharged. For example, chlorine. So you will be adding less chlorine in this case. And they are generally very good removing all the ions, whether they are uh, uh, phosphate ions, nitrate ions, any ion that has a charge. Obviously, that's why they are called ions. We apply these fields in a manner that they go to oppositely charged electrodes and they are removed from the flow, from the feed. Therefore, we get rid of these nutrients before the water is released. Now, one last thing that is more practical in terms of application at a large industrial wastewater treatment or municipal wastewater treatment is that these processes normally are modular and scalable. You can start small and keep on expanding as you see the value of these uh, technologies. Now, understand this. This is a technology that is slowly being integrated in the system. Um, and every technology has a challenge that they have to face in terms of openness to adopt. For example, I'm going to tell you this, which is this example has nothing to do with wastewater treatment in India, and this is kind of relevant in terms of current news, and you will understand like, okay, there is a reason which are beyond benefits and disadvantage of the technology, and that could make it um, applicable at wide scale and not applicable at wide scale. When the US was expanding, and I'm talking about 200 years ago, from East Coast to West Coast, the people who were there, labor who were there, they only thing they knew at that time was cutting woods, and they were really good with wood, carpenters they were, and they started using wood as a building material. So houses were built using wood because it was cheap, it was there. Generation after generation, people gained the expertise and the infrastructure set up in a way that wood were cheap to process and to build houses. Even though concrete came in and people realized that concrete has really good properties as compared to wood in certain situations. For example, fire. Los Angeles fires recently, we that whole neighborhood were gone. But concrete has a fire resistance quality. But despite that, the people and the labor skill, they do not have as much uh, skill set to work with concrete. They still prefer wood, and there are other parameters because it is insulator and other thing. So sometimes when you are trying to disrupt the industry and trying to bring in the new technology, there is going to be challenge when people who may not have the skill set to work with the new technology. And that's why we call it the barriers that are there to expand any technology at a larger scale. So electrochemical technology is at that stage. It has benefit since not many wastewater treatment plants have implemented it at large scale. People don't have the experience, they don't have the comparative study data to present, and therefore everybody thinks like, okay, is it going to be suitable at large scale or not? Now, generally, the idea of electrochemical technology is introduce current into the wastewater, let electrodes and the pollutant interact with each other. And the product hopefully is going to be that these complex pollutant will either be broken down and settle down or will be converted into something less harmful. That's the idea. There are different examples for this. For example, over here, if we are trying to apply this thing in association of conventional wastewater treatment, this could be used, electrochemical treatment processes could be used as a pre-treatment where raw sewage or raw wastewater is brought in. We apply the electrochemical processes, and effluent from that process goes to the main treatment or the post treatment in this case, where biological treatment processes will take place and the water will come out with better quality, which could be used for various purposes. So that's the main idea in this thing. Uh, and I just want to state this thing one more time that electrochemical processes are not there to replace conventional wastewater treatment uh, plants. They are there to make them better. So let's talk about all kinds of options that we have. Generally, uh, one of the main uh, option that is out there and most used option is electrocoagulation. It is going to work just like coagulation process. In coagulation process, we add coagulants, chemicals, which are going to help make pin flocks and remove the charge. And then since that charge is gone, these particles end up hitting each other. They end up making pin flocks, and flocks get bigger, and then they settle down. That's the idea of flocculation, coagulation, flocculation. Now, in this specific case, that initial action of coagulation is triggered by the tiny metal particles that are introduced into water because the electrodes are being forced because of current uh, to introduce the tiny metal particles in the solution. And the electrical current itself takes care of the charge. So it neutralizes the charge on these many of these pollutants. And then they coagulate and they separate out from the wastewater. It is effectively applied in labs and field conditions, and there are tons of publications where you will see electrocoagulation has been used for heavy metals, organic matter, suspended solids, and oil. Um, Specifically, if you are looking for the names, you will see that lead, arsenic, chromium 6 are some of the heavy metals for which you will find a lot of publications online. And then there are suspended solids which were extracted from industrial sludge, textile dyes, oil and grease. It worked great over there. We had petroleum refinery wastewater. There are a bunch of publications out there. And then pathogen and bacteria. Now, there are current naturally is something that will give cell destroy the cells at the cellular level. But in addition to that, magnetic field and electric field, they are a really good disinfectant. They kill bacteria and viruses directly. So what happens, a combination of all chemistry and electrochemistry, electrical current, you will see a better effluent coming out. Specifically, since Surat is a textile hub, you would see that electrocoagulation has been used in multiple case studies for methylene blue and reactive black 5 dyes. This is the setup of electrocoagulation, and you will see the theme of setup is kind of same pretty much. You will have two electrodes that will be introduced. You will have a DC charge that you will apply, and in some cases you will see hydrated cations being formed. There will be some coagulation action taking place, and then you will see some generation of hydrogen gas and electron. They do flotation, and in some cases you will see all that contaminant uh, after coagulation and flocculation will be floating at the top. In traditional wastewater treatment, you will see, drinking water treatment, even for that, you will see after coagulation, flocculation, flocks get bigger and heavier and they settle down at the bottom. In this case, you will see them floating around where they can be removed uh, from the top. So here is a device that you see. This is all the electrodes. They have the current. They are being this electric current is being applied, and you can submerge those electrodes in different bigger contaminants, uh, bigger containers for contaminant removal. This is before and after picture of the lab experiment, where you can see that after the electrocoagulation, all the contaminants which were scattered everywhere, now they are converted into a little bit different, uh, smaller byproducts, and they are floating right there, which can be removed easily. Second variation or second uh, form of electrochemical technologies is electrochemical oxidation and anodic oxidation. Now, we are zooming in a little bit on one aspect of uh, uh, electrochemical processes. Here we are paying attention only on the oxidation and specifically anodic oxidation, where we will have anode which will be made of platinum, titanium, or boron doped diamond, and which will create strong oxidizing agents like hydroxyl radicals. And these are strong radicals that will do the job of breaking down the organic pollutants. And you will see that they are very effective in terms of pharmaceutical pollutants, pesticides, and even persistent organic pollutants. If you are looking for specific examples, you will see that uh, pesticides, specifically atrazine, lindane, and in terms of pharmaceutical, ibuprofen and paracetamol, and these names are just common household uh, knowledge. The amount of these pharmaceuticals, whether discharged in our human waste or human urine, or because they are being dumped later on if they get expiry, uh, the concentration of these specific chemicals is rising in wastewater. And uh, our anodic oxidation and electrochemical oxidation does a very good job in removing. There are other endocrine disruptor pollutant, and these are the polluters which target your biological processes in your body, meaning it will the endocrine disruptors are the ones that will change the way that your body works. So if you are female, you will start showing symptoms of a male body, meaning you will start having facial hairs. And if you are male, you will have less facial hair. You will see suddenly the body is changing, something similar to what females body go through. So they are really dangerous. Uh, this anodic oxidation does a great job in removing BPA and hormonal byproducts that are going to be there. Uh, I see a couple of hands are being raised. So if you please note down your questions and share them towards the end, I would appreciate that. I won't be able to see all the hands that are being raised right now uh, because my focus is on this screen. I'm not looking at the side screen. So please excuse me for that. I think Dr. Taylor will do a great job in terms of taking questions from you afterwards. Uh,
Definitely, sir.
So moving on with next, well, I need to talk about specific chemical reaction. And again, it's going to be similar to what we have seen before. However, the specific intermediate steps that are going to be, they are electrooxidation, electroreduction, oxidation, reduction, they both happen at the same time. It depends on what you are looking at. And then there's going to be electrodissolution of the compounds that electrodes are made of, and then there is going to be electrodepletion. But most of the time, it's the oxidation radicals that are the ones that are going to uh, do the main thing. This is one example of the setup that you can see. It lists all the information and the dimension and everything. And there are multiple such applications that are out there, and a good number of publications have listed good amount of success in there. The third one is electrophantom process. Again, it is a variation of the first two. In this case, you will have iron and hydrogen peroxide that will be mixed in the wastewater. And that combination of electricity, iron into the system, and hydrogen peroxide, that does a more effective degradation. Even hydrogen peroxide alone does a good job of killing some of the bacteria and treating some of the organic waste, but a combination of all three is overall more effective. The pollutants that are removed, you can see that the pharmaceuticals there, the industrial chemicals are there, and pesticides, and then dyes. Again, these are, you're seeing is theme that is out there when it comes to targeting certain kind of wastewater coming from industry. Here you will see uh, a setup specifically if the Fenton reaction that is taking place, you have hydrogen peroxide, you have iron particles, they are going to be getting oxidized, and then OH will react with pollutants and will give you the product. So basically, even if you don't understand the chemical process that is taking place and your focus is only on looking at contaminant in the effluent, you should be able to uh, experiment at small scale. There is a data that will provide you more in-depth information in terms of each specific reaction and the pollutants that are being removed. These technologies that I talked about, normally they work in a cluster, meaning you do not apply just one, you take bunch of them in different combination and treat that whole cluster as a pre-process, and you get better effective results. You can see you have to go through a certain uh, uh, steps that are going to uh, be based on iteration. You will do one setup for your unique characteristic of the waste. If it is not going to work, you remove one unit, you bring in other type of unit, and after a couple of three iterations, you should be able to have a very effective electrochemical treatment of the wastewater. Now, the previous one was electrochemical oxidation. This one focuses on cathodic reaction, cathodic uh, reduction, and you will see the contaminants that are going to be treated are going to be um, nitrates, perchlorates, and heavy metals. Chromium is something that is effectively being removed. Chlorinated solvents, PCE, TCE, perchlorates, they are some of the well-known contaminants that do very well under this kind of technology. Uh, in terms of explaining what is happening within this domain of electrochemical technologies, specifically chemical reduction technology, electrochemical reduction technology, you will see that there are a bunch of organic compounds that are removed. There are metal complexes that work with these organic compounds. Uh, and then there are benzene family chemicals. All of them are broken down at the cathodic reaction and they are removed from our wastewater stream. This new part, I say new, but it has been there for some time. Before I did my uh, dissertation on capacitive deionization technology, I used to work on a project that was implemented at uh, my research lab, and that was using magnetic field to kill bacteria. In that study, we realized that it's just not the magnetic field. Electric field, like common sense says that over there, was also killing the bacteria. So just the electric field alone or the byproduct that are going to be formed in water because of electrical current, all of that combined usually ends up killing uh, the bacterias and viruses. For example, over here, if your byproducts happens to be chlorine or a family of chlorine, ozone or hydroxyl radicals, they are collectively are going to kill uh, organisms, and that is one of the key component in addition to all the uh, anodic oxidation, cathodic reduction, all those things are taking place. But since current is being introduced into the water, and if we can make chlorine during that reaction, or if we can make ozone from in that reaction, uh, the side reaction of these things, which is called as electrochemical disinfection, they will end up cleaning your wastewater more effectively. So some of the pollutants that are removed using electrochemical disinfection, there are bacteria and viruses, which there's a whole family of bacteria, E. coli, hepatitis A virus. You can just have a list of the bacteria. And then there are uh, uh, protozoas uh, and harmful bacteria, organisms that make us sick. There are antibiotic resistant genes, which are getting even harder to treat, even with specialized uh, technology, because antibiotics, great, they do a great job, but once you have genes that are resistant to antibiotic, they become so sturdy, so resistant to all the treatment technologies that are thrown at them, that they do not go away. So in those specific cases, electrochemical disinfection does a great job. Uh, and this is basically has been used at municipal level, as well as the wastewater coming from hospitals. As you know, by the name itself, this is kind of more suited for that kind of wastewater. Again, you can see that combination of SCLO and CLO ions doing the magic of killing the bacteria, in addition to the effect of the current, and uh, all that results into a better uh, effluent quality. Now, this picture describes the whole working scenario. It tells you that where you can apply this kind of electrochemical disinfection. It starts from tap water, which we drink, and all the way to the black water, rainwater, you name it. It will work on all kinds of water. Most of the time, mechanism is going to be chlorination, because we produce chlorine through electrical oxidation reduction, electric field, which is going to kill. And in some cases, if you can bring in the magnetic field because of electricity, that will also be the one mechanism that will help. The factors that will control the efficacy of your treatment most of the time is going to work on the focus on the material that are being used for electrodes, specifically anode. Then reaction condition, how fast and how slow the chemical kinetics is, and what are the target microorganisms. And at the bottom right corner, you are seeing different variation of electrochemical disinfection. And these are different acronyms that you're seeing. So don't worry if you don't know these names, as long as you know that it is electrochemical disinfection. And since other things will happen, and based on that, they are giving the name. So if you have a highly porous uh, electrode in there, then in addition to electrochemical disinfection, electrochemical oxidation, there's going to be adsorption reaction that will take place. And that's why they are calling it electrochemical disinfection dash adsorption. So these are just different names that are given based on the chemical reactions that are going to take place. Capacitive deionization is something that I really like because I invested a lot of time in it. My PhD dissertation is on it. And in general, if I can give you all a simplistic idea in terms of what this thing is. So understand that a capacitor in high school physics, we learned that bring two metallic plates closer to each other, apply DC voltage plus and minus on these metallic plate. They will create electrical field in between. The current will not pass because there is no connection, but that gives capacitor stores electricity. So capacitive deionization works exactly like this. But we fill this capacitor, we call it, with water that needs to be treated. Now, water ideally is not conductive for electricity if it's pure, but in terms of saline water, in terms of wastewater, it is going to be full of all kinds of impurities and ions. So what happens as water is flowing through between these two electrodes, which are highly porous, uh, the positively charged pollutants go towards negative electrodes, and negatively charged ions go towards positive electrode, and water that comes out on the other end is cleaner, without even considering other chemical reaction that takes place. It works mainly on charged species, so basically ions. As long as it's ion, it will work. In many cases, bacteria are also removed because bacteria has many of the bacteria has negative charge on them. So it does a good job in terms of removing bacteria. So these are some of these ions that have been removed. My study, all the studies that we did, even my undergraduate, my PhD students, we've targeted many of these ions that are listed here. So the electrodes that I talked about, they could be made of carbon cloth, activated carbon, carbon aerogel, carbon nanofoam. There are different types of carbon, but understand this, that the more porous uh, electrode is there, the better the performance is going to be. Now, in one of the case studies, we actually took the carbon electrode, coated this thing with highly conductive metal. It performed good, but what happened? It covered some of the pores, so effective area of these electrodes was reduced, and therefore the capacity for them to remove things through electroadsorption was reduced. So before we jump into, most of my experiments were focused on aerogel and carbon nanofoam. This is a man-made material. It's not found in nature. We make it in the lab. It's really, really conductive, very light, heat resistant, and strong. For example, you can see that picture on the top left. This thing is standing on this uh, barley, and you can see that it's so light that it's not even bending this the tiny hairs of that. Light can pass through it, so it's really, really porous, and it's yet is strong that it can withstand all the weight that is being. It's expensive, at least it was expensive about 15 years ago when it was new in the market. Now there are different ways and cheaper suppliers that will that you can buy easily. Different forms of carbon aerogel and nanoforms. They come in all shapes and all particular possible combinations. Most of my studies, we use it in paper form. You can make it in the lab. We didn't make it in the lab. We bought it from the supplier of the cell. But normally you have a precursor, you do hydrolysis and condensation, let the gelling take place. We make sure that we take the wet gel, you super critical dry it, and as you are drying it, once the dye product comes in, you burn it in the presence of different gases. And when you are burning this carbon, this dry gel, based on the gases that you use in that environment, it is going to give you different porosity. And all the water, all the structure, when it's gone away, leaving behind the skeletal, which is very, very porous, that's carbon aerogel. That's how we use it. In terms of a explanation how it works, you will see that water, these are two electrodes shown on other side. One is negative, one is positive. Brackish water is coming in, and all these ions that will be removed. Let me see. So you can see that uh, depending on their polarity, they will end up being removed from the flow. And soon what will happen, these electrodes that are on opposite end, they will be fully saturated, meaning the positive electrode removed all the negative ions it wanted to, or it could remove. There's no more space anymore for the new ions. In that case, we change the polarity and we bring these ions back into the solution by doing the reverse flow. That's what the basic concept of capacitive deionization is. For example, over here, this is a simplistic study from one of my student. We prepared the plexiglass, and as a base, we used carbon electrodes on top of that, and we measured the conductivity. With time, you can see that x-axis being in second, and conductivity represents how much ions are there. Higher the conductivity means higher quantity of ions are there. And as water was passing through these cells, the conductivity of the solution was going down with time. And that's a proof that, okay, all the metal ions which were in the liquid, they have been they were being removed. Depending how many cells you have it in series combination will give you the quality of a treated water proportionately better. In some medical applications where ultra pure uh, water was needed, uh, they were able to use in one of the national lab uh, about 120 cells, and they were able to remove pretty much everything from the water. We didn't do that experiment, so I will not talk about that. And when the cell is fully saturated, you reverse the polarity as shown over here, and the things that were absorbed, all the ions, they come out into water and they are washed. So you start with pure water with zero or very little conductivity, and this will be the brine that will come out. Now the issue is not all the ions that have been absorbed, they come out. Some of them are going to be trapped deeper into the pore size of your material. So pore size and target ions, that matching has to be just right for it to work in effective manner for absorption and desorption reactions. This is the setup that we used, fairly simple. You have a CDI cell. We are pumping water from one end. This is salt water supplying going inside, and the same water comes out here on other end, and we are measuring the conductivity based on. You can do the same multi-pass thing, meaning this water can be taken back. This is single pass experiment, but you can do the multi-pass experiment as well. And these are the benefits and the cost, the effectiveness that we were able to explore. Some of the parameters that you need to be very careful in choosing, and I'm not sure how much time I'm using, but I will try to finish up very quickly. Uh, you will see that specific surface area, which is going to be surface area uh, available for ions to come and attach to. So that plays a very specific role. Pore size distribution, like I said, if pore is too small and ion is bigger, then you will have less area for them to be removed. If target ion is small and your pore size is too big, great, but it will go really deep into the pore and will not be able to come back out. In that case, you have to change your electrode material often. And since if you are using carbon aerogel, it's kind of expensive to use and throw. We want to regenerate again and again. So you have to match. You will have to work with supplier and ask them that I want this range of pore distribution uh, for this kind of contaminant. Conductivity of your uh, material, that is also, we want higher conductivity because it's all electrical based. We want stability. These electrodes should be stable for multiple cycles. They should not just break down. Fouling should not happen of these electrodes under wastewater conditions, and the cost obviously should be less. One of the more interesting experiment revolved around coating these carbon electrodes with our metal. So we took simple carbon electrodes as like shown over here. Then we coated this thing. The positive electrode was coated with thin layer of gold. We use that electro vapor deposition method where this I'm saying carbon, the gold foil was vaporized and we had a carbon electrode on top of it. All these vapors were getting deposited on carbon. It was kind of complex process, but we wanted to explore the possibility, and we saw how just one electrode, changing coating with that. What was the result? Then we did both electrodes coated, and then we did negative electrodes coating. So in both cases, results came out to be different. And if I had time, I'll share more information. One of the paper that I will list here just only talks about the reason behind different uh, uh, efficacy of the treatment. I believe the very first one says asymmetric capacitive deionization. This is the one that was referring to this kind of one because we did asymmetry. This is symmetrical. Both electrodes were coated. In this case, bottom left and right, you can see that only one was. So this paper talks about that. And then there are other analyses over there. Even the second one talks about that. Now, moving away from CDI, and CDI has been used for uh, ships that are going to stay at the sea for a long time. They take highly concentrated seawater and they do a combination of reverse osmosis as well as CDI to bring the water to the potable level. If you are military applications are there, but commercial applications have been there as well. Now, this CDI technology is also being used with membrane. Just like I told you before, it's a combination of technologies. So you have semi-permeable membranes, and some of them are electrical conductive. We apply current on them, and then we bring in the microbial cells. Now you are seeing it's going to be cluster of technologies and action that will take place. So this is electrochemical membrane processes, its own category. It include you will see that the same thing happens in electrodialysis. I just gave you an example of applying voltage directly to the membrane, using membrane as one of the electrode. So two actions takes place: sieving action because of the sieve size of membrane, and then there is electrical action that will repel certain kind of electrodes even reaching that particular membrane. So dual action takes place in this case. Some of the pollutants that have been removed using EMPs, sodium chloride, obviously salt, sea salt, phosphate, nitrates, zinc and nickel, they have been, fertilizer industry, wastewater has been treated effectively using these uh, electrochemical membrane processes. Now, this, for example, over here, you have these two electrodes, positive electrode and negative electrode. If you see the dotted line, the blue dotted line, it says monovalent and anion exchange membrane, and the red dotted line is another membrane, which is cation exchange membrane. And if you'll notice that the blue water is the feed water where organics are there, they do not go through these membrane. But these membrane allow a certain kind of ions to be removed, and all the reddish water that is shown, that is brine, which has been rejected, and the cleaner water, feed happens from the bottom and the cleaner water comes from the top, which is processed water, and it is supplied. So there is about 90% reduction of the concentration in this membrane process, which is assisted by electrical technology. This is setup of that. You can do the multiple cells in one thing, and the more cells you have, the better efficiency and the better flow you can handle. The one limitation in these processes is the flow Q. So far, they have been applied at the pilot scale. For larger scale, you need to have many of these cells in parallel for you to deal with higher Q. And then there are the fuel cells, the bacteria cells that are in combination of the membrane technology. They do the same kind of thing. For example, over here, they will bring in the action that is taking place because of the bacterial there's going to be carbon dioxide that is a product of their respiration, and then acetic acid metabolism reaction takes place, and that is assisted by your uh, electricity. This is one example of microbial fuel cells being applied at a larger scale. I believe this model was 1,000 liter. It was effectively dealing with 1,000 liters. But as you can see that even 1,000 liters required a little bit uh, larger footprint. Uh, Now, since this is in early stages of development in terms of applying this technology to the industrial wastewater, but since then, more publication came out for it to deal with larger quantities with smaller footprint. Now, so many technologies in combination. Let's compare uh, and see what are the key pollutants and these technologies are targeting, and what are their example applications in one slide. Even though most of them were already discussed, you can see that landfill leachate treatment is effectively treated using electron Fenton process, and the list goes on. CDI being mainly used for desalination and removal of nutrients. Uh, and then we have electrocoagulation that deals with dye removal. So basically, this is just a summary of the one of the first few slides that I presented. When you look at electrochemical processes, you have to understand that these technologies are in early stages of development, not because they are new technologies. When I say this, I say in context of their integration into large scale wastewater treatment plants. And these are conventional wastewater treatment plants. The risk and the cost that is associated with these technologies is a entry barrier for them to be effectively implemented uh, widespread in a widespread manner. So now the question is, who will be able to apply them? Uh, if every business and every municipality is thinking in terms of cost and treatment operational challenges, they probably will not take the risk. Now, if more stringent uh, effluent standards are forced upon these wastewater treatment plant operators, that would force them to think about that. Okay, my waste effluent doesn't have a very good effluent quality, or pharmaceuticals in my effluent are exceeding the limit. Then they will be forced. That will be a motivation for them to try new technologies, even if they have to spend a little bit more. So that's where, at the crossroad of conventional wastewater treatment and integration of new technology, that's where we stand right now in terms of our uh, progress in this area. So this is the end of wastewater treatment using electrochemical processes presentation. Uh, I appreciate your time and patience in terms of staying with me. Now at this time, I will take all the questions you may have for me.
Thank you so much, sir. Mr. Abhay Nagle, you had a question. Mr. Abhay Nagle?
Yeah, can you hear me, sir?
Yes, I can.
Yes, yes, you are audible.
First of all, thank you very much, sir, for a very, very informative presentation. I'm really highly impressed. I'm having about 45 years of technical experience, and yours was one of the best technical presentations I have ever had. I have two small little questions. I mean, is the anode always sacrificial? And if yes, does it add as a pollutant? And if it adds as a pollutant, how to treat it? That's my first
So
question, sir.
Thank you, and I appreciate your kind words. Uh, So, anode being sacrificial in nature, that is not always true, but in most cases it is sacrificial. However, the risk of these metals contributing to pollution is less because these are electrically and chemically controlled. The moment these tiny micro level metals come into the action, they are assisted by chemical reaction and electrical action, and they end up getting uh, processed within the treatment. Now, what will happen? Because of coagulation and flotation, your byproduct that comes out as a slurry or as a sludge, that may have a little bit higher concentration of the anode material if your anode is sacrificial in nature. But in the effluent, it's not going to be the case. But the sludge that will be removed from these reactors, that may show higher concentration of metal.
Thank you. Can I ask another question, sir?
Yes, go ahead.
Yeah, I saw that it helps in removing microplastics. Now, microplastics, they are electrical current phobic, and so how does that really work on an electrochemical reaction?
So yes, thank you for taking my attention to that. Now, what happens? This microplastic inclusion of microplastic in one of the pollutants that are removed is actually for specific technologies where we bring in the membranes which are coupled with electrochemical processes. So in some cases, the sieve action which is there, which is going to be because of these uh, the membranes, that is still the primary action that keeps these microplastics out of our effluent. So I would have to agree with you on that. The electrical process is not the driving force behind it, but the sieve, mechanical sieve analysis, when we are using sieves assisted with electrical chemical forces, uh, the mechanical action takes care of the plastic, not the chemical or electrical reaction, if that makes sense.
Thank you. Thank you very much, sir.
Mhm. Any other question? Somehow. I'm...
Sir, may I ask?
Yes, go ahead.
Sir, myself Siddharth. Thank you for sharing your deep insight into this particular subject, sir. Sir, I have two questions. The first one is, sir, what are the major, critical factors which affect the efficiency of the electrochemical disinfection process?
So there are multiple factors, and in most cases, you need to understand that the whole concept is based on how much electrical energy we are using. If we end up using too much electrical current, then electrical oxidation potential, reduction potential, they come into play. And then there is the stability issue of electrodes that also comes into play, and the cost becomes an issue. So you need to understand that the chemical reaction and the condition under which these reactions take place. So electrochemical disinfection, uh, as long as you are trying to stay within a certain applied potential, will work fine. And there are guidelines for that based on the nature of electrical, the wastewater waste found in wastewater, or pollutants in wastewater. You can choose your applied potential. Normally, it's far less, uh, because we don't want to create a side reaction uh, in an effort to treat the water.
Okay. Thank you, sir. My next question is, sir, sir, like you said that electrochemical oxidation process can be used for treating the wastewaters emanating from the hospitals. So, sir, can only electrochemical oxidation process used for treating hospital wastewater, or they can be used in conjunction with the conventional methods?
Yes, so all these statements that are made here, they are with this understanding that just electrochemical process alone won't be able to treat the overall wastewater coming from any of these sources. For example, in case of hospital wastewater. So hospital wastewater most of the times is going to have a lot of suspended solid, lots of colloidal solutions. It may also have biological species in there. So we have to understand that electrochemical processes is just one treatment or one step of the treatment for overall treatment. So if you are using conventional method, great, but consider using electrochemical as one of the treatment step that this water will go through.
Okay, thank you very much, sir.
Dr. Taylor, I cannot hear you. You're saying
Yes,
something,
yes,
but
I'm sorry.
yeah.
Yes, I'm sorry.
Uh,
Is
um,
there any? Okay,
may I
sir.
may I ask question?
Yes, please.
Sir, is there any commercial plant available based on for the treatment of wastewater using this
So
electrochemical method?
So there are a combination of technologies that have been used in US. The CDI technology has been used in areas where salinity has been a big issue, and electrocoagulation has been used as one of the treatment step uh, of metal plating industry, where the wastewater has high concentration of all kinds of metal ions, but these are at a smaller scale. I think there are two of them in United States where they are using electrocoagulation as one of the intermediate step that takes care of wastewater. And then the water goes to other traditional ways of filtration, reverse osmosis, those kind of things. Since this water comes from industry, it has a unique characteristics of having metal ions in larger quantity and less organic compounds. For example, it's not comparable to sewage treatment, if that makes sense. And I will try to give the names of those plants. Let me find them out. I don't remember it as of now, but I should be able to provide those uh, specific case studies that were done on this case.
Sir, I do have one question.
Yes,
That
please.
is this technology efficient enough to treat refractory CODs?
For that, the verdict is still out. So that the reason I say because not much uh, work has been done specifically in refractory CODs. So I won't be able to answer your question with greater confidence here, because unless more studies are out and the data is out for us to look at and say that okay, this has worked well in this case. So as of now, I don't think there is enough data out there that will support this claim that it is going to have a satisfactory performance on COD specifically. And that's why I did not include COD in any of my target contaminants.
Yes. Okay. Okay, sir. Uh, Dr. Rahul Karale, you had one question, right, in the chat box. You may please proceed to ask. Dr. Rahul Karale.
Hello, am I audible?
Yeah.
Yes, you are audible, sir.
So very nice session. Uh, uh, I have one question regarding about the life of the electrode. How means what is the capacity? How we can decide about the electrode as in relation to the degree of treatment required, and what limitations does it impose on this overall treatment?
Thank you, Dr. Karale. Now, understand out of 7, 8 options that we discussed, uh, the the survivability of electrode or the duration for which an electrode can be used effectively is different for different options. For example, capacitive deionization CDI technology that I worked on many times, we were able to regenerate the same carbon electrode without any coating on it for more than 100 times. It was kind of expensive. We just wanted to uh, saturate it, and when it stopped doing the treatment, meaning the conductivity of the treated water was not going further down, we used to stop and reverse polarity. We used uh, other options as well. Our water that we were using to flood this thing or wash this thing, if I can say that, was higher temperature, and we used multiple mm, process of diffusing the capacitor. We were able to regenerate this thing for more than 100 times with very little degradation in their performances. So for CDI, you could use it more than 100 times. For sacrificial electrodes, it will depend on the the rate at which it is being consumed, and that will depend on the concentration of pollutants in the wastewater and also the amount of electricity that is being applied. But in my opinion, you would still be able to get a decent life of electrodes uh, in case of sacrificial electrodes.
Okay, sir. Can I ask one more question?
Sure.
It's concerned with the electrophenton process, which you mentioned. Sir, how it is different from the photophenton process? Because both generate hydroxyl radicals. So, is there any difference in the rate kinetics, or how we can decide among which method to be used as far as
The
time constraints and degree of treatment?
So I think in terms of actual chemical reaction, there's not much difference. But the only difference that you will see is the motivating or energy source that makes it happen. In photo case, you the energy that comes that is coming because of photons. In this case, energy comes from electricity. So that is the difference over here. The actual reaction which takes place is going to be similar. So in terms of what makes this reaction happen, you're just looking for the source of energy. In this case, happens to be electricity.
Okay.
Okay, thank you.
Uh, okay. Mr. Atish More.
Yes, sir. Atish More here. So my question is, at what temperature the pollutant are get melted in a water medium, and how much energy is required?
So
Am I audible
can
to?
you repeat your question again?
So at what temperature the pollutant are get melted in the water medium, because it's the wastewater, and how much energy required for the removing of that more pollutant?
So temperature doesn't play much role, a bigger role in this. There is a little bit chemical kinetics involved with the temperature, but it is not going to be the driving factor or controlling factor. And the energy that is required, if you can calculate, is going to be different a little bit on different options. For CDI, we apply about 2 to 3 voltage, and in most cases, it's going to be less than 2 voltage. And the current is going to be very small amperes, meaning it could be less than 1 ampere or around that. So you can see that 2 voltage, 1 ampere, or even less than 1 ampere, if you do the product, the actual energy requirement in case of CDI is very little. Now, on the other hand, for other chemical processes, it is going to be a little bit more. Not CDI is the most efficient in terms of technology, but in case of sacrificial electrodes, other oxidation reduction processes, that energy requirement is still low. You will be applying around 15 to 20 volts, and the amperage is going to be around 10, 15, and it varies for different options. So that should give you an idea how much energy we are talking about. And again, water temperature doesn't play as much significant role. Yes, it helps in terms of kinetics, but not significantly. Theoretically, it does, but practically, it doesn't.
Okay, sir.
I suppose there are no more questions. Or do we have any questions? Okay, thank you so much, Sanjay sir, for your valuable time and it was a very insightful session, something new to learn. Thank you so much for this session.
Thank you
Okay,
very much for having me, and I want to thank you, Dr. Yogesh, and you for inviting me and to be a part of this experience. And just want to let you know that uh, anytime I can connect with Surat or things that are happening with Surat, uh, it just brings a lot of happy memories for me. So this is my way to staying in touch with my alma mater, even though I know Pacific is not where I went to, but it just takes me back to SVNIT and my days in Surat. I hope Surat. I'm told that Surat has changed since 2000 significantly, but I have not been there
yes,
since 2000. But planning to hopefully be there this December because we are going to celebrate 25th anniversary of our graduation uh, in Surat.
that's good to hear. Yeah, that's good to hear. So whenever you plan to come to India, we will arrange an offline session of yours.
Yes, definitely.
Okay, okay, sir. Thank you so much for your time and patience and your knowledge sharing session. Thank you so much.
Thank you. I appreciate the opportunity.
Okay, sir.
Bye.
Bye, sir.
Mhm.
So, dear participants, that's all for today. We shall be meeting tomorrow again on the same link at 6 p.m. So make sure you join the session by 5:55 p.m. We will be having two sessions tomorrow, 6 to 7:30 and from 7:30 to 9. Okay, and the link for the attendance has been shared in this chat box. Kindly fill that link for today's attendance. Thank you so much once again. Good night.
Thank you so much, everyone. Good night.
Good night, sir.
Thank you, sir.